who is PhD from National Physical Laboratory, and she's now working as a postdoctoral fellowship in non-destructive evaluation laboratory at the Department of Civil and Environment Engineering, University of Missouri, Columbia, USA. She is actively involved in determining the acoustic properties of materials, detection of defects in welds, and development of NDE technology for civil infrastructure applying ultrasonic testing. Her research interests includes non-destructive testing and evaluation for industrial and metrological laboratories for quality control and damage detection of materials. She is professional member of American Society of Non-Destructive Testing and life member of Ultrasonics Society of India. Thank you very much, ma'am, for accepting our request and delivering a talk on this very complicated topic to be in a simpler way. Thank you very much. We have with us our Honorable Shri B.N. Dixit, Director, sir. Sir, would you like to speak 2 words, please?
Yes, Astoji. So today chief guest Dr. Kalpana Yadav madam, who is presenting the concerned topic of today program. Sri Astos Agrawal ji, Director Legal Metrology, Government of India, the organizer of the program. Very interesting to listen the topics, the ultrasonic importance for the testing of the materials and other related field in the legal metrology and the metrology with the various institute and in the industries as well as various institute and so many things. So I think that today lecture will give the lot of knowledge to we people, the organizer of the programs as well as to the people who are visiting and attending these very programs. I wish for the success of the programs and wish for the nice presentation of Dr. Kalpana Yadav. Thank you, Astoji. Thank you.
Thank you very much, sir. Thank you for your kind and motivating words always. Thank you very much. Over to you, ma'am, please.
Sir, am I audible first?
Yes, ma'am. Yes, ma'am. Very well.
So thank you so much for having me and giving me an opportunity to talk about my research here. I hope I'm not gonna bore. Yeah, I wish I am not going to bore you guys a lot about like talking a depth in the depth of my research. I am just gonna give you a lot of more like layman in layman
language.
Yeah, in layman language. Yeah, I'll try to do my best. So
there must be the night in there must be night in US now right now. You must be
yeah. Yeah, it's no, I'm good. It's 11:36 right now here, PM.
Very good. Please continue, ma'am. Yeah. Please. Thank you.
Yeah, thank you so much. So the topic of my research is role of ultrasound in industries, metrology standards, and NDT. So I'm going to talk about those. So these are the outlines of my research of my presentation, where I'm going to talk about ultrasound and NDT and their applications, advantages and disadvantages, and how ultrasound is produced into the materials, and how many types of ultrasonic waves are there, and how ultrasonic testing works, and what is the basic principle of that. Along with that, I'm going to talk about the instrumentation and how data is acquired in ultrasonic testing, and how ultrasonic metrology is contributing in like nation, and how ultrasonic calibration standard are calibrated in the laboratories and industries, and what is the approach of calibration. And other than that, I'm going to talk about a little bit of my research. I'm not going into depth a lot. I'm going to start with the introduction of ultrasound. As we all know, ultrasound is a sound frequency above the human hearing range. As we human can hear only from 20 hertz to 20 kilohertz, but there are some so just like a speaker, music that lies in the audible sound. But ultrasound is above beyond that frequency, so that's above like 20 kilohertz. But some animals birds like bat, they can hear those higher frequencies. They are more than 20 kilohertz. They are very sensitive. Our like ears are not sensitive to that much of the frequency. And infrasound is a below frequency, below audible sound, that's below 20 hertz. That's infrasound. Some elephants and mice can hear those sounds also. So ultrasonic waves require a medium such as liquid, solid, or gas to propagate. They cannot travel into vacuum. They are very much like light waves, but they are not exactly like light waves because they cannot travel in the vacuum, but light wave can travel into the vacuum. So these waves can easily get reflected, refracted, and absorbed into the materials. And if talking about what is non-destructive testing, so non-destructive testing is an approach to detect defects or any kind of discontinuities and abnormalities inside the material without causing any effect to them. We are not going to break them or anything, but we are just going to assess them without affecting their integrity. So NDT is a critical tool for preventing maintenance and quality insurance, ensuring safety, reliability, and efficiently it used in across the industry. So ultrasonic testing is a powerful tool of a non-destructive testing evaluation, because with the ultrasonic testing we are not going to affect the material. We are going to check that material, so that ultrasonic testing falls in the category of non-destructive evaluation. So talking about the applications of ultrasound and NDT, so ultrasonic waves are applied in various industries, including the manufacturing and process industries, in medicines, also in domestics, in civil, marine communication, and wind turbines, and many more. If you see around around you, you will find ultrasonic NDT everywhere, like in bridge and roads. In the bridge, you so like the steel bridges, the bridges that they manufacture with the steel or some kind of concrete, the abnormalities and defect can be easily find out with this testing. And train in railways, similarly for the material testing in aircraft and defense, in petroleum and gas to check those pipes, and sometimes it is used to check the adulteration of the liquids also, and in wind turbines and marines and medical equipments to uh, medical equipment to clean those equipment at higher frequency. Ultrasonic NDT is everywhere around. So if I'm going to talk about like specifically in industries, in defense, railways, manufacturing, as in last slide I discussed. In medical, it's therapeutic and diagnostic, largely due to the fact that non-ionizing, because as we know, the X-ray is also a non-destructive testing, but that's ionizing testing. It does have like a harmful effect on human beings, but ultrasonic testing doesn't have that much of limitations in terms of ionization. So in R&D for the liquid characterization, material assessments, and spectroscopy, and in power, in petroleum and gas, these testing is used for the transmitting higher energy to find out specific density, to find out if there is any adulteration or not in those materials or not. Guys, you can interrupt me if I'm very fast in between somewhere. If you have any question or something, I'm just going to continue with my slides, or you can ask question at the end of my presentation if you have any. And nowadays these testings are also basically used in the food industry to determine the characteristics of the food to check the food quality, if there is any kind of abnormalities, or if there any kind of a problem with the food or something. So that can be also these days researchers are doing some research on that ultrasonic testing can be used for that thing also. So there are three ways the way ultrasonic waves can be generated. The most commonly used wave is a piezoelectric effect. So in piezoelectric effect, you have a disc, you're going to apply some kind of electrical force on that, and that force will cause the vibration in the disc, and that disc will cause the generation of ultrasound. That way that generated ultrasound will going to be transmitted into the material. And there is another way like magnetostriction effect and electromagnetism effect. They are electromagnetic effect where the where magnetic field plays an important role in generating ultrasound, and these methods are basically used when there is a geometry of the material you are going to assess is very complex, or it's the surface is not regular, and where there is not conditions are not like in very harsh. When the conditions are like it's very hot, you cannot access those samples with the piezoelectric effect. Then you need a transducer that can have a lift off of something, so you don't directly touch that specimen with the transducer. So these methods are used when there is a harsh environmental conditions. So there are like multiple type of waves depending on the like application. You can select which one you are going to use. So the most common used ultrasonic wave is a longitudinal wave, or sometimes it's called compressional wave. So when like the direction of the particle and direction of wave is going to be the same in the material, that's called longitudinal wave. And shear wave is a direction of the particle is going to be the perpendicular to the direction of wave. And surface wave are waves that can be generated on the surface of the samples, and plate waves are when material where, plate waves are waves whose particle motion lies in the plane that contains the direction of wave propagation and the direction perpendicular to the plate. So if we see the like we compare all these waves, we see the longitudinal velocity. If we consider a material made of steel, that material is going to be the highest longitudinal velocity is the fastest velocity. So if you see here at the right side of your screen, longitudinal velocity in steel is mentioned 5890 meter per 5890 meter per second. But if you compare that the same velocity, but that is going to be shear velocity, it is going to be half of that longitudinal velocity, and surface velocity is lesser than even shear velocity. So it depends if you are like if you're so these waves are used depending on if you are like as accessing your sample at your defect is at particular angle or something, you cannot launch longitudinal frequency there. You need some like angular waves. So in that case you use shear waves. If your flaws are near the surface of the sample, so you're going to use surface wave. And if your material is more like a plate and it have like very lesser thickness, so you're going to use plate waves in that case. So it depends on the principle you are going to, it depends on the application of the like the specimen you're gonna do that. So that's how you choose which wave you're going to use with ultrasonic testing. So what is ultrasonic testing? So the propagation of waves in the material has become useful tool for the study of different materials. Different material means aluminum materials, steel materials, or any kind of metals. They can be accessed with the ultrasound. So ultrasound is basically generated. So here, whatever I'm going to talk about, it's more about the piezoelectric effect, because that's what I did in my PhD, and that's what I am doing right now. So all my waves were generated with a piezoelectric transducer. So piezoelectric transducer convert one kind of electrical energy into ultrasound vibrations, and vice versa also, because inverse piezoelectric effect also is there. So ultrasonic testing uses high frequency 1 to 15 megahertz ultrasonic energy for the measurement and estimation of location and destruction and damages in the metal, and also for the thickness measurement. So by UT, sometimes we say ultrasonic testing as UT. So surface and internal discontinuities such as void, cracks, hole, all those can be evaluated with ultrasonic testing. And ultrasonic testing can be basically used by two methods. It's a single transducer method, that's also called pulse echo method, and other than there is a two transducer method, that's called through transmission method. And these two methods further can be categorized in two categories. Either you are going to use as a directly contact with the sample, or you're going to put your sample in some kind of liquid. Because earlier I told you about that, like ultrasound cannot travel in vacuum. So while you are assessing your samples, you need some kind of medium to propagate ultrasound in that material. So you need some kind of medium. So if you are using contact method, you are going to put some kind of like a liquid gel or something in between as a couplant. When you are putting your sample, when you are using immersion method, you are putting your sample into the water or something. So in that case, your water is gonna act as a couplant. So the basic principle you can see here in the GIF at the right side. If you see, here is a ultrasonic test unit. Sometimes most of the like all the time it's called ultrasonic pulsar receiver, where you can like control your pulsar parameters, where you're gonna like electrical signal and everything, and receiver part is going to receive those signals. So here is a transducer that transducer have a piezoelectric disc. When you are applying electrical signal to this transducer, that transducer is gonna generate that transducer have a disc that's going to vibrate, and that vibration will cause generation of ultrasound. So now these, if you see here, these can travel along the sample. If the sample have some kind of defects or anything, you're going to see that defects or signals in the oscilloscope or whatever display device you are going to use. So ultrasonic wave are basically generated by the electrical force. The vibration in the disc of transducer causes the generation of ultrasound, and typical system of ultrasonic testing consists of a pulsar receiver, ultrasonic probe, sometimes it's called transducer, and display device. That's mainly oscilloscope. So right, so the left side of this setup is a basic principle of ultrasonic contact testing, where ultrasonic probe is making direct contact with the reference standard. So but you need to put some kind of liquid couplant. Sometimes we use oil, honey, for the to having like proper contact with the sample. So like there should be like maximum energy transmission in the sample. So that's why here is the ultrasonic flow detector and digital so ultrasonic flow detector is used for the generation of ultrasound and reception purpose, and digital oscilloscope is going to display your signals. So if we want to measure the ultrasonic velocity in the sample, you can see the formula here. Thickness is equals to velocity into time by 2. Time by 2, this 2 contributes in the, like, the same transducer is going to transmit the signal inside the sample, and same transducer is going to be receive those signals. So there is going to be twice that transducer is covering that path twice. So that's why it's 2. And if you can measure the thickness of the sample, and these waves, they are, when they are going to hit the surface of the sample and the back surface, the reflection you can see, and you can measure that time by the oscilloscope, and that's how you can calculate the velocity of ultrasonic waves, and that's how you can see. So if there is going to be any defect inside the material, you will see the first transmission. I'll explain that thing in the next slide. I think I do have that graph where I can explain it more. So I'm going to talk about, like, first, what are the advantages and disadvantages. So this ultrasonic testing has many advantages in comparison to disadvantages. So because only one side of access is required. This is the most important part of this. If you are using pulse echo transducer, pulse echo means you are using single transducer. You don't need another transducer for the receiver's purpose. So from the transducer you are transmitting your signal, from that same transducer you're going to receive that signal. So you need only one side of access of that material, and this technique is sensitive to both surface and subsurface flaws, and minimal sample preparation is required. You don't need to prepare those samples before testing them. It's just like they should be clean, and not like properly clean, just like there's supposed to be no like a liquid couplant or something, or like mix of those couplants or something. So higher accuracy in determining the location of defects and estimation of the size. The dimensional measurement can also be made with other than the flow detection of these. Like if you are doing if you want to check a petroleum pipe or something, like measuring the thickness of that pipe is very much harder in case of if that specimen is very big, or that the size of that petroleum tank is very big. So you can have the dimensional measurement with the ultrasound very easily, and there is no hazardous radiation that makes it more adaptable to use. So along with the so this technique has so many advantages, but this technique also have so many limitations. So like good surface finish required. If the surface of the sample is going to be irregular, the transmission of energy is not going to be perfect. Like it's not going to be transmitted perfectly. So there is going to be some loss in the energy, and you are not going to get better signal when they are getting reflected from that sample. So the good surface finish is required, and coupling agent is also required. You cannot test without like coupling agent. Coupling agent plays a better role for transmitting your energy also, and reference standard is also required, because whenever you're gonna check your sample on the field, you are going to get some kind of amplitude reflection from that material. So to test if those amplitude reflections are correct or not, you're gonna compare. You need a reference standard to compare whatever energy you are getting from the sample is comparable to reference standard or not, to make a decision. So also the high and trained skilled person is required for this testing, because the signals you're gonna see, they seems same like from the front surface, from the back wall, from the it's just the amplitude is going to be different, so you need to figure out which one is which. So that's why, and it takes a lot of like exhausting work to do, and accuracy get compromised while working with the complex sample, because having rough and irregularities in the shape, so there is going to be a lot of energy loss in the sample. And so if you are going to get a lot of noise, and if your signal is coming from some irregularities or defect, you're not gonna see if it's a noise signal or if it's an actual signal from the defect. So yeah, the accuracy get compromised while working with the complex samples. So the main key factor of this ultrasonic testing is ultrasonic pulsar receiver that plays an important role in the generation of ultrasound and reception of ultrasound. So the pulsar generate electrical pulses, and they supply to the transducer to produce ultrasound, and transducer having piezoelectric element in the probe head that generates short burst. So this is some kind of like electronics. You need to figure it out, what frequency you're going to use, what like gain you are going to use, what type of signals you're using, right? So all those can be controlled with the pulsar receiver, and it's a very like much important part of that ultrasonic testing, because if you're using lower frequency, you're using like some certain lower parameters, you're not going to see your signal. So that device should be optimized up to the application, whatever you are testing, if it's up to the mark or not. Like all the parameters should be taken care of while you are adjusting the frequency and everything. And the receiver, the same device have a receiver section where you can like you receive your signals, and by receiving those signals you can increase your gain, and you can adjust a lot of things, gain or filtering thing. If you don't want some kind of frequency in your signal, so you can filter them. That all thing is going to be like selected from pulsar receiver. And transducer is a device that will generate and receive those signals based on the pulsar settings. And oscilloscope is going to show you the signals here. So to generate like ultrasonic pulses, you need ultrasonic pulsar receiver, and all the properties and acquisition can be then further studied with that device. So like how ultrasonic data is acquired, there are three methods to acquire ultrasonic testing data. So it is called A scan, B scan, and C scan in industries, and like on site in field they basically use A scan and sometimes B scan, but I'll say like most of the time, 90% of the time they use A scan. So A scan is a, if you are accessing your sample, it's a particular point you are accessing with the transducer. You are not gonna move your transducer, so it's a particular one position you're gonna. If you're going to move to the second point, it's gonna be second A scan. But so it's a display of the received ultrasonic signal as a function of time on the oscilloscope. But while you are doing B scan, it's a linear scan. You can say it's a line scan. You move your transducer along the length of that specimen, so it's gonna give you cross-sectional view of the test specimen. If you see here in the figure, so yeah, I was talking about like what you're gonna be reflected from your sample. So if that signal is going to look like this in the you can see the A scan overview. It's going to be amplitude versus depth, so or amplitude versus time. So the initial pulse is from the surface of the sample, and if there is in between any defect in the sample, you're going to receive that defect echo. And from the back surface of the signals, you're going to have a back surface. And with so you have that gate settings. Gate is going to capture whatever you want to capture. Like I want to know what is the time of initial pulse, so I'm going to set my gate at initial pulse. So you can move those gates along that length, and you can have that data in the B scan. So this B scan is from basically one of my tests. I was testing a rail specimen that had a surface and a notch at the corner. So you can see we cannot see how it was oriented, but still you can see there was some notch and there is a surface signals. But if you see here a pictorial view of artificially created defect sample that's I made for the C scan testing. So C scan display C scan is going to be a 2D scan of the plane. So it just gives, so if you see here artificially created a sample, and the right side of that shows the C scan overview. So this is a C scan. So you can see how that defect is oriented in the sample. So like if you want to know more in depth how is yours, how is your defect is, how is its orientation is, so you can do C scan for the better evaluation. So talking about the ultrasonic metrology plays a crucial role in providing traceability to medical and industrial equipment. it's basically consists of industrial metrology is going to talk about like UFD, ultrasonic flaw detector device, that is used for the defect detection on site to check if there is any kind of abnormalities and material qualities. And there is a lot of ultrasonic reference standard that are used against those testings. And in the medical devices, just like ultrasonic power, focal length, intensity, and for the pressure and hydrophone calibration. So basically there are 2 or 3 main parameters we access when we do those testing. So that's called ultrasonic velocity, sometime, and ultrasonic transit time, and attenuation. So if I say what is attenuation, attenuation is just like when your wave is propagating inside the material, it's just gonna cover some length. So over the time the energy get dissipated, so your wave get attenuated. So like it's just losing its energy over the time. So that's called attenuation. So when we just want to know like how much energy is getting dissipated because of the material or something, when we want to study the properties of the material, then we do ultrasonic attenuation. When we want to know if there is any defect or not, we do ultrasonic transit time measurement. If we want to know if there is any kind of we want to know about the characterization of the material, we also do ultrasonic velocity measurement on the samples. So this is picture is from CSIR NPL where I did my PhD. So this is primary ultrasonic power measurement system that this system is used for the like calibrating ultrasonic power, how much transducer is going to emit how much transducer is going to have that power in the transducer. So like the activity has indigenously developed primary ultrasonic power measurement facility used for the measurement of total time averaged ultrasonic power generated by the transducer, and the frequency range for this was 0.5 megahertz to 20 megahertz, and uses the radiation force balance principle. I'm not going to talk about a lot of those scientific stuff, but here is the ultrasonic calibration standard. If you can see here, they comes in various shape and sizes depending on the things you are going to do on the field. So here is a IIW block, and some like these reference standard block comes in different shapes and sizes. The type of standard is used in depend on the NDE application, and the form and shape of object is being evaluated. So if you're gonna do like pipe inspection or something, pipe surround thing, so you're gonna use flat bottom hole. But if you're doing a thickness standard, are most likely used for the flat or curved, used for the pipe and tubing application. The calibration block contains notes. I think it should be notch, not notes. Side drill holes and arc to create amplitude and time relationship. So like what you do on the field, test your material, whatever you are testing. Suppose you are testing a bridge, so you are putting your transducer on that bridge and you are getting some signal reflected from that material, and so for that you need a reference standard block. Whatever signals you are getting, if they are in correct form or not, if they are the energy of that signal is same or not, so you just need the reference standard block to calibrate that stuff before running your actual test. So ultrasonic metrology activities and technologies at CSIR NPL. So CSIR NPL is responsible to maintain the national standard, we all know, in the field of ultrasonic and in NDT also. So just like we do have, like they do have primary ultrasonic power measurement, IIW V1 and V2 reference standard block. I'm going to talk about this IIW V1 block further, and step wedge ultrasonic pulse velocity measurement. I think one of my colleague presented some of his presentation before. He was talking more about the accuracy for the ultrasonic pulse velocity measurement. And cylindrical FBH block can be like calibrated. So they do have like a lot of standards for different references, different reference standard have different standard code. So ultrasonic flaw detector and testing of all ultrasonic facilities are available for the measurement of propagation of velocity, impedance, and attenuation for solid and liquids also. So this is ultrasonic. In this slide, I'm going to talk about like ultrasonic flaw detector. So this is a ultrasonic flaw detector that is most widely used in the ultrasonic NDT in the industries for the assessment of the materials. And this system already have that ultrasonic pulsar receiver and display device, but over the time these devices get deteriorated. So to confirm and to check the capabilities of this system, we calibrate this system with the IIW V1 reference block. So this IIW reference block we are gonna test this UFD against with the ultrasonic IIW IIW reference block, and this IIW reference block is mainly designed and proposed by the American Society for Testing and Materials. And they so in India we do have a standard like IS 490 for this IIW, but here like people follow ISO 2400. They do have like same type of clauses, but some of the like acceptance criteria are different. They are not exactly same. So this IIW blocks should be made of fine grained low carbon steel with low attenuation coefficient, and brushing and hardening are also prohibited for the surface of the block. So this is the comparison between like Indian standard and ISO standard. ISO is an international standard, and IS is an Indian standard. So they do have a clauses for like materials and dimension, which kind of material should be and which kind of dimensions should be. So they do have like different clauses about like material surface, finish heat, treatment, variation in attenuation. So if you see here, the acceptance level for the Indian standard, it says low or medium carbon steel it should be. For the international, it says steel or equivalent grade would be accepted. And variation in attenuation is allowed plus minus 1 dB for the this material. And the international standard doesn't talk about the variation in the attenuation. And the ultrasonic velocity is a major difference here. Like acceptance level of IS Indian standard is plus minus 1 meter per second, but acceptance level for the ISO is plus minus 30 meter per second. And the thickness of perfect, so all these like they all are same, other than this ultrasonic attenuation and velocity measurement. And both for the both of this, the roughness of the is equivalent to 0.8 micron. And ISO doesn't include any requirement for the plastic inside, and IS include parallelism and perpendicularity, that is not also not included in the international ones. So like how parallel is your that reference block is going to be, and how that the grain are aligned perpendicularly, so that is also included in the Indian standard. So there are various approaches to do like calibrating that device. So the first approach, so I did a lot of like testing in my PhD. So if we can like automate those calibration approaches, so you need so what I did, I just confirmed with three methods with 3 methods if I'm getting the same variation in uncertainties or not, like how much variation is there. So like ultrasonic velocity calibration using ultrasonic flaw detector, and thickness of reference standard block where you can measure your velocity the way I explained it before in the slides. And ultrasonic velocity calibration using transit time. As we know, like velocity is equals to distance upon time. So if you want to measure velocity, you can measure the transit time and the distance thickness of the sample. So if you measure thickness and transit time from the sample, you can have ultrasonic velocity. And we do compare the ultrasonic the uncertainty in the sample. And so as IS also include ultrasonic attenuation. So ultrasonic attenuation is attenuation is measured in the immersion approach. So you are going to put your sample into the water, and then so that water is also need to be maintained. So yeah, so here if you see here ultrasonic velocity, this V shows the sound velocity in water, and T is a temperature. So if you put your sample into the water, that water velocity is supposed to be maintained, because it does also get affected with ultrasound. So if you will maintain the temperature, you can measure the ultrasonic velocity, considering that the temperature was set to 20 degrees Celsius and ultrasonic velocity was measured at 1480 meter per second. And according to ISO, like the laboratory temperature should be maintained. So yeah, so if you're so there are like multiple type of probes or transducer used in the industries to test those specimen. So here is a like angle beam transducer that shows the sensitivity of the calibration block. So there are like different side drilled hole. These different side drilled hole, if you launch your frequency, so this transducer is particularly launching a wave at 45-degree angle. And so the angle beam transducer are typically used to locate or size flaws which are oriented non-parallel to the test surface. Suppose your transducer is normal to the surface, it's going to transmit the signal at that perpendicular. It's going to not like give energy at the angle. So you need a angular probe, or you can do like mode conversion. You can like if you have a longitudinal wave, by the Snell's law you can convert your signal into different mode. So yeah, so this is so in like on site they use angular beam transducer to test their samples. and they do those like testing at 45 degrees, 60 degrees, 70 degree, and all those transducer are commercially available in the market for the those testings. So like here, if you see so there are like many ultrasonic testing. I'm mostly talking about ultrasonic immersion testing and ultrasonic contact method, but there are ultrasonic EMAT testing, phased array testing, and all these ultrasonic concrete testing, ultrasonic air couple testing, laser ultrasonic testing. These all testings are based on the ultrasound, where they are going to generate ultrasound. But the generation of ultrasound and the reception of ultrasound is going to be different. While the principle is going to be the same, where you are generating ultrasound inside the material. So like suppose if you are using laser ultrasonic testing, what you're going to do, you are going to launch your laser on the specimen, and that specimen is get heated, and those heating thing causes vibration in the particles, and that vibration causes generation of ultrasound. These are the different method you can have. Like if like if you have a complex specimen and you have irregularities in the specimen, you cannot use ultrasonic contact method, then you need alternative of that method. In that case, you can use ultrasonic EMAT testing, where you don't need to make direct contact. And phased array testing is I'll say it's more upgraded version of ultrasonic testing. So here we are using only single transducer having one like disk that's generating single pulse and receiving the same pulse. But in phased array testing, there is going to be multiple transmitter signal and multiple receiver signals. So you're going to have like a lot of signals that can be analyzed based on the time delay, like time difference while you are receiving that. So it depends on the application which testing you are going to use. So mostly I'm talking about here is ultrasonic immersion testing and ultrasonic contact method. And you can so if you're generating like different kind of modes, you can tilt your transducer in the water, you can rotate in the x and y z axis, and you can make perpendicular to the sample, like the way you want to access that sample. So this slide shows the my research in PhD, where conventional ultrasonic immersion scanning system consists of multi-axis motor. So this is ultrasonic immersion testing, where this is a immersion tank. I don't know if you guys can see my cursor. I don't think. So here, no. So this is ultrasonic immersion tank, where you put your ultrasonic probe, and this ultrasonic probe can have angular, translational, and linear motion, and that is going to be connected with the pulsar receiver. And this pulsar receiver is going to be connected with data acquisition card that is going to acquire your data, and that is going to be controlled with the personal computer having a software to control that data acquisition card, and that is connected with the RS-232 or LAN communication. And this multi-axis motor is so basically a servo motor based systems, so they can control the motion of this probe, and they can be rotated or moved along the way you want to, like the amount of scanning you want for the testing. So what I did, so this is a conventional ultrasonic immersion scanning system people use in industries, and like here also they use in our lab for the testing of, for studying the acoustical properties of the material. But what I did in my PhD, the development of indigenous immersion scanning C-scan system, where we removed ultrasonic pulsar receiver and data acquisition card, because you don't need to control those two things, and you can have so this device already have all the parameters you need to adjust in the data acquisition card, because you have all the settings in the pulsar receiver, and that pulsar receiver is widely used on site for the testing of the materials and testing like bridges and components. So what we did, we connected this ultrasonic flow detector with the immersion tank, and this ultrasonic flow detector was controlled by a computer software. We developed a software for that, the complete arrangement here schema for this, and that also that water temperature measurement device. We used LM35 sensor to monitor the water in the tank to see if there is any variation in the water temperature or not. So if it's gonna, so it can record like all the at certain time the temperature of water to see if ultrasonic velocity get affected while you're doing your measurement or not. So this all setup was so the basic idea was to doing that, because we do calibration with the manual, we do calibration at manual, like people are going to use a scan. They are going to do manual 3 scans. If they are measuring ultrasonic velocity like manually, they are going to do 3 scans, and then they're going to average. With this device, you can like automatically have that data, and you can decide like what area you want to scan. Everything you can define. Like it's not going to be 3 measurement and taking average of that. You can scan the complete specimen within some of time, and you can have that data. And in the C, so this is going to give you C scan, so you can easily see how much variation is going to be in the thickness or in the velocity, whatever parameter you are going to use. So here is like a graphical user interface of that ultrasonic C scan system, where you can control your like home position control is for the motion axis, where you can control X, Y, Z and A, B for the tilt and angular motion. And for the you can select scanning area, like how much range you want to scan for the samples, and what step you want. And you can control your UFD settings like energy, PRF, that's pulse repetitive frequency, damping and pulsar, all the receiver frequency. And you can set your gate, whatever you want to measure inside that gate, and the velocity section for the water velocity and the velocity of the like material. And you can start like move, set parameters and then move, and it will show you start scanning. And once your scanning is done, it will show you like data acquisition completed, and you can stop that. And so here if you see, there is an aluminum block. They are also like reference standard in our lab. They are used for like aerospace industries. They use these standards. So what I decided to do a scanning of 20 by 20 to 50 scanning area. I selected that, and if you see here, I was measuring the thickness. And from this C scan system, from the C scan image, you can easily see like these different color in the C scan image is showing how much variation is there in your rod. So if you see the blue portion in the start of that 0 to 50, between the 0 to 50 x-axis, you see the thickness of that this side is like 20.01 to 20.03 or something, not more than that. You can easily see how much variation is going to be there in the thickness. So if you can correctly monitor your thickness, you can correctly monitor your ultrasonic velocity also by this method, like an ultrasonic attenuation also. So you can see by just looking at that, and that thing is not like possible with the manual testing. I will say you cannot see the image, you can only have like number of measurement or something. Sir, I think you are muted and you were saying something. Okay, I think you're not talking to me. So yeah, this shows the when I did like ultrasonic attenuation measurement. So like you can see here easily like how much attenuation and is there in the block, the area you selected. So you can have like this formula ultrasonic that formula was already there in the program. I put that, so it's gonna like pick eco 1 and eco 2, and it's just gonna average this, and this that can calculate ultrasonic attenuation easily in the samples. So the system developed is based on UFD and acquired the required parameter only rather than entire raw file. You don't need to like have all the data. The data you're just gonna be interested, you can acquire that much of data. And this greatly reduces the size of the C-scan files. Basically, these files, when you do a lot of testing, these files are in the gigabytes. To avoid that, and for that, you need a data acquisition card that have a better sampling rate, like 250 or something. So this automation system also reduces those limitations, and this system reduces human efforts, human errors, and reduce cost and time saving also, and there are less chances of the error. So here in this slide, I'm going to talk about the research I'm doing here currently. It's so here so here I'm in civil department, and my professor works more closely with the bridge people, and those bridge people follow like AWS standard code for accessing the bridges if they do have any kind of abnormalities or not. So they do have this standard, also AWS standard, and this is so steel is a major component used in the construction of bridges due to high strength and ductility, and approximately 1/3 all bridges in the United States have like superstructure formed from the steel. So this the AWS standard used for the assessing of these steel bridges, and that AWS code says the calibration standard, the IIW block, the one I already like explained before, the material under test have supposed to have similar acoustic properties, like they're supposed to have velocity and attenuation calibration similar to whatever we are going to test on the field. But and the refracted angle, you're going to launch like different angles. Like they do a lot of testing at 45 degree, 60 degree, and 70 degree. So they say the refracted angle, signal amplitude in the calibration standard are assumed to be same as the side drill hole of the similar size and depth in the material under test. But what we figured it out. This is not how it this is not how it works, because the material you are going to use on the field is going to be different the material you are using as a reference standard block, because there are like different processes to manufacture those steels, and those manufacturing process affect ultrasonic velocity. The way you are going to produce those steel, that's how their ultrasonic velocity is going to be affected. So so like in on field they use radiography, and so radiography testing is used, but it's not sensitive when the defects are at deeper depth. This testing is applicable when those surface are like those defects are near the surface of the sample or near the surface. So UT is used for that mostly when those defects are at a deeper depth. And the calibration standard and the material under test have similar acoustical properties. It doesn't make any sense, because if the issue with the material is that if velocity in the material under test is different than the calibration block, if you are launching your frequency at 70 degree, it's not going to be 70 degree because it's going to be 73 degree. If you know the Snell's law, like velocity is going to be if your velocity is different, your angle is going to be different, and if your angle incident energy is different, the transduction efficiency is going to be different. And you are launching your frequency to like some shear waves, but that mode is going to be converted to surface wave. So there is no relationship between 0.06 inch side drill hole in the IIW block, and because discontinuity is going to be lost in that case. And if material under test is anisotropic, so velocity is going to be different in that calibration block. So there is going to be a lot of like factors. Beam splitting is going to be there, and destructive interference is going to be there, and beam steering is going to be there. So all these parameters causes not to have like that IIW block as a calibration block on the field. So we tested a lot of steels. They are manufactured like with different waves. TMCP is a thermomechanically compressed like processing, T1 plates, QT quench tempered steel, and stainless steel. And we figure it out. Not all the velocities in the rolling direction and transfer directions are same. So the using IIW doesn't make any sense. So this is my research is about like improving the anisotropic method of ultrasonic testing to test those bridges against the standard reference block and have a different approach. If you are using following that AWS code, only like having that IIW V1 block as a reference, you are going to compromise with a lot of things, and those results is not going to be accurate. So yeah, these are few my references. Thank you. This was my presentation. If you guys have any
कुछ इक्विपमेंट भेजे हैं, कुछ कह रहे हैं बाद में शेयर करेंगे, जैसे बड़े-बड़े इक्विपमेंट हैं.
Thank you very much, ma'am. Thank you very much for your brief and very interesting presentation. I hope that it will be very useful for all our participants. With your permission, we will place it on our website. Your presentation as well as the video which we have recorded today, it will be available on our website for the benefit of the participants. Thank you. Thank you very much. Can you please, Santosh ji, can we make all the participants the panelist so that we can take few photographs for the social media?
Yes, sir. Yes, sir.
Atul ji, if anybody wish to ask anything, you are most welcome.
Yeah.
So ma'am, we will place it on our website. Kindly share me your presentation, which will be available all the time.
Mm-hmm. Okay. I'll share
Thank
that by tomorrow, maybe.
No issue, no issue. Either on WhatsApp or mail, as per your convenience.
Okay.
Thank you very much. With this, I would like to thank all the participants, ma'am, for your kind help us supporting us in a short time. You were ready to make the lecture. Thank you very much, Dikshit Saab and all the participants. Thank you. And I